Hey guys, in this section we're going to talk about solving systems of equations. And we're going to talk about solving systems of linear equations, even though in college algebra you might actually talk about solving systems of nonlinear equations as well. We're just going to focus on systems of linear equations. And so an example of a system of linear equations would be, suppose you had two equations. One could be x plus 2y equals 3, and the other one might be 2x minus y equal negative 4. This is actually said to be a 2 by 2 system because you have two equations, 1, 2, and you have two variables, x and y. So two equations and two variables, that's a 2 by 2 system. Now, this system here, sometimes it's more convenient to let your variables be subscripted variables like this. So let the variables be x1, x2, and x3. And that way, if you have a large number of variables in a problem, you don't have to, try to search for different letters. You can just let them be x1 through x whatever you need. Now, this system is a 2 by 3 system because it's 1, 2 equations, but yet you have 1, 2, 3 variables. So 2 equations, 3 variables. And then this is a larger system, and I won't show you this until the very end. This is sort of an optional section. This type of system is kind of optional for an intermediate algebra course. So, but you have, here you have 3 variables, x, y, z, and 3 equations. So this has 3 equations and 3 variables, so we call it a 3 by 3 system. Now, in practical applications, the systems of equations could be very large. So, for instance, consider all the variables required to launch a rocket. Time, velocity, temperature, direction of x, direction of y, direction of z, acceleration, momentum, friction, air resistance, etc. In this lecture series, I will mostly work with smaller systems like those I just showed you. So the 3 methods that we're going to talk about are going to be the graphing method first, and then I'll talk to you about the substitution method and the elimination method. So let's go ahead and get on with the graphing method here. Okay, so the idea for the graphing method is basically you just want to graph the 2 equations. So if I want to solve this system here, I need to graph the equations. Now there's 2 ways that I can go about graphing this equation. I could solve for y, and then I could use the slope and the y-intercept to graph it, like we learned in earlier sections. Or I could find both the x and the y-intercepts and plot the points. So I'm going to do it that way. So for this one, if I let x be 0 here, then I know that y equals 8. And then if I let y equal 0, then I would solve this equation 2x equals 8, so that would give me x equal 4. So the y-intercept is the point 0, 8, and the x-intercept is the point 4, 0. Now on the next one, if I let x be 0 and solve for y, 3y equal 9, so y would be 3, so the y-intercept would be 0, 3. And then if I let y be 0 and solve for x, I get 9 for x, so 9, 0 would be x. So pretend like you don't see these graphs here for now, and let me just plot these points. So 0, 8 would be right here, and then 4, 0 would be right here. So I would grab a ruler and I would draw this line through those 2 points. Then I need to graph the other line. Generally you want to label the lines, okay? And then I want to graph the other line, and it goes through 0, 3. So 0, 3 would be this point here, and it goes through 9, 0, which would be right here. And then you grab your ruler again and draw the line through those 2 points and label that line. And then notice that the lines will intersect, and the intersection of the line is of the 2 lines is the solution to your system. So they intersect right here. Now, as long as you use nice grid paper and you draw these accurately, you should be able to identify the intersection as 3, 3 units to the right, and then up 2 units. So the solution would be the point 3, 2. And by the way, you can check the solution just to make sure. Let's just check it real quick. So if I plug in 3 for x and 2 for y, let's see what I'd get. 2 times 3 is 6, plus 2 would be 8, so that one checks. And then 3 plus 3 times 2, that'd be 3 plus 6, and that equals 9. So that one checks. So the answer is the correct answer. Now, one of the problems that you run into with this system is, what if instead of intersecting at 3, 2, what if they intersected where x was 2.9 and y was 1.9? Well, it would still look like it's at the value 3, 2, but actually the answers would be those decimal values. So that's why we're going to eventually move on to a better system, a better method to solve these, substitution and elimination. Okay, moving on. When a system involving only two variables, there are 3 distinct possibilities. The lines could intersect at one point. That's what happened in our previous example, and it will give us a unique solution, and that's the point where they intersect. In this case, the system is said to be consistent and independent. So remember that. Now the lines could intersect at infinitely many points. Now that is usually true when the lines are the same line. So both equations represent the same line, and in that case every point on the line is a solution. And then that's considered to be a consistent and dependent system when that happens. And then the lines may not intersect at all, and that would give no solution, and in that case the lines would be parallel lines, and in that case we would say we have an inconsistent system. Okay, so let me give you 3 examples here. Now this is the one I just did, so I'm not going to go over it, but you can see that this one, it intersected at a unique value, and so you only got one value. And now what I wrote up here was, this is what you would do if you were going to graph it using the slope-intercept form. So, but anyway, I've already graphed it, so we won't go through that. All right, so anyway, this gives us a unique solution, and so that's a consistent and independent system. Now, this system, if you solve the first equation for y, by the way, you could graph these using the x and y intercepts too, but I'm just going to show you the other method here. So if you solve this for y, 2x plus y equal 8 is y equal minus 2x plus 8. And so the y-intercept, actually it would be way up here somewhere, so the y-intercept would be way up here at 0, 8. And then you could use the slope, and you would, go down 2 over 1, go down 2 over 1, down 2 over 1, and so forth. And then you would get more points, and you draw the line through the points. Okay, well, it turns out that the second equation, if you solve it for y, you get the same equation. So it would be the same line. So since these two equations represent the same line, then every point on this line here would be a solution. And since there's infinitely many points on the line, there's infinite number of solutions, and we call that a consistent and dependent system. Now, the only difference between the second one and the third one here, on the third one, when you solve for 2x plus y equal 8, you get y equal minus 2x plus 8, and when you solve this one now for y, you get y equal minus 2x plus 3. Okay, well, these two lines have the same slope, but they're different intercepts. One intercepts way up here at 8, and the other intercepts right here at 3. And then when you draw the lines, you get parallel lines. In that case, there would be no solution since there's no point of intersection, and we call that an inconsistent system. Okay, here's another one, and you can pause the video here and check this, but you notice that if I let y be 0 and get x, I get 3, 0, and if you let x be 0, you get 0, negative 3. And so it intersects at 3, 0 and 0, negative 3 here. And then on the other one, if you let y be 0, you get negative 1. And if you let x be 0, you get negative 1. So this one goes through -1, 0, which would be here, and 0, -1, which would be here. And so if you draw the lines through that point, then it'll intersect right here. And so the solution is actually at 1. I didn't use grid paper here. It probably would have been better with grid, but if it goes over 1 and -2. So this point of intersection is the point 1, -2, and you can certainly check that. Okay, so here's 3 examples solving by the graphing method, and again, you can freeze the video if you need to. But on this one, I found the x-intercept and the y-intercepts. The y-intercept is 0, 3/2, which is right here, and the x-intercept was way over here at 3, 0. So you'd have to, plot it out here somewhere, and then you draw the line through those points. And the other one goes through 0, 4, which is up here, and then -2, 0, which is here, and then you draw the line through those points, and then you can see that they intersect at the point -1, 2. Now these next two, you can see that this goes through the point 0, -3, and 3, 0, but so does this one. So both of these lines contain the point 0, -3, and 3, 0. So the equations represent the same line. So in that case, you have infinitely many solutions in a dependent system. And then for this one, the 3x minus y equals 6 goes through 0, -6, and 2, 0. So that would be here and here. So you draw the line through those points. And then y equals 3x minus 2, if you find the intercepts for that, you'll see it goes through 0, -2, and the point 2/3, 0, but they have the same slope. So these lines would be parallel lines, and they have no solution. Okay, and so that's an inconsistent system. Now, vertical and horizontal lines, the graph of x equal k, where k is a constant, that's a vertical line, and when y equal k is a horizontal line. So for instance, the line x equal -3 is a vertical line containing the point -3, 0, and y equal -3 is a horizontal line containing the point 0, -3. So if I wanted to graph this system, first of all, I could find I could graph this using the intercepts. When y is 0, x is 3, so that would go through, let's see, this must be the axis here. So that goes through, here's 0, 3, or 3, 0. And then when x is 0, it goes through -3, so that would be down here. So you would draw that line through those 2 points. And then y equal -1, it would be the horizontal line that goes through the point 0, -1 here. So you draw the line through that point, and then you find the intersection from the graph, which is the point 2, -1. And then, of course, you can check them. So again, that's the graphing method for solving the solutions of these types of systems. And as long as this system has only 2 variables, x and y, the equations can be thought of as lines. So that's how you solve them, by graphing. Now the next section I'm going to cover is going to involve solving these types of systems by the substitution method.